Hello and welcome to Maths with Martin. This is the second video in my exam style question series, a series of videos that are going to get you super prepared for the upcoming A-level exams, or if you're not doing A-level exams this year, just be good to do a little bit of maths anyway. This video is going to be all about probability. You can find all of the questions in the description below. My recommendation would be do the questions first and then come back here and we'll go through the solutions. I picked probability because I know sometimes students will neglect the applied part of the course, or maybe not neglect, but maybe not spend as much time as they would proportionally with the applied as they would the pure. But applied still is a third of your course, and you don't want to just wait until your pure exams are out of the way and then have a week to just cram all of the applied. So we're going to get started with a little bit of applied early. And if you are a pure fan, don't worry, I've got you covered. There will be a little bit of pure that makes an appearance in here as well. Let's get to it then with our first question. So we've got here a game shows a number 1, 2, 3, 4 or 5. Maybe not the most exciting game you've ever heard of, but the random variable C represents the number the game shows and has the following probability distribution. Okay, so the game's going to pop up either 1, 2, 3 or 4, and it's got all of these assigned probabilities. So this is what this probability of capital C equaling little c means. Basically it just means the probability that the event of it landing on a 1, event of it landing on a 2, and so on. So you've got all the probabilities. Now, we've given you 1, 2 and 3, but what we haven't given is the probability of 4 and 5. That's just called A and B. So you're told here that A and B are constants. And we're also told the probability of getting a 4 is twice the probability of getting a 5. And that should be enough information for us to find what A and B are. So the first thing I need to note with probability is that the sum of all the probabilities will add up to 1. Okay, the sum of all of the probabilities will add up to 1. And that's going to be, that won't be necessarily a bullet point they tell you. So that is something that you need to think about when you're solving these types of. So let's get writing down some equations. So we know that a third plus a quarter plus a sixth plus A plus B, all those probabilities are going to add up to 1. So adding up these fractions on the left hand side, that's going to come to 3 over 4, and then we can take away that 3 over 4 from both sides, and we get that A plus B equals a quarter. Okay, so at the moment I've got one equation, but I've got 2 unknowns. That's not going to be enough for me. So what I'm going to need to do is use this second bullet point, that the probability of getting a 4 is twice the probability of getting a 5. When you get questions like this and you get these bullet points, this isn't the examiner trying to catch you out or anything. It is going to be something that is useful to the question. So let's make use of this second bullet point. The probability of getting a 4 is twice the probability of getting a 5. What this means is the probability, let's use some of our notation here, probability that C equals 4 is twice the probability that C equals 5. Okay, now the probability of getting a 4 is A, the probability of getting a 5 is B, so A equals 2B. And then what I can do, if A equals 2B, I can substitute that, if we just call that 1 and we call this 2, I can substitute in A equals 2B into my equation there, so just subbing that into equation 1. I get that 3B equals a quarter, and therefore B equals 1 over 12. Knowing 1 over 12, that B is 1 over 12, I can then substitute that B equals 1 over 12 into the first equation, A plus B equals a quarter, and I find that A equals a sixth. So that's part 1 dealt with. Let's look at part 2. This is going to be a fairly quick part here. The probability that C is greater than 2. Okay, that's where I was find probability that C is greater than 2. Well, that just is going to be the probability that it's 3, 4, or 5, because we're not including 2 here. Okay, this is a discrete distribution here. There's only 5 values in total that it can take. So if it can't be 2, the next number up that we can get is going to be 3. So we just want to work out the probability of a sixth plus that probability of getting a 3 plus probability of getting a 4 plus probability of getting a 5. So that's going to be a sixth plus A, which we just found out to be a sixth, plus B, which is we just found out to be a 12th. And then we're going to add that up to get 5 over 12. So there's a part B to this question, so let's look at that next. Okay, so part B, I've just included the table again, and what I'll do is I'll just cross out now that that's A. We know that A is a sixth. We know that B is 1 over 12. So we're told that the game is played 10 times. If a number selected is greater than 2 at least 7 times, the player wins a standard prize. If the number selected is greater than 2 at least 9 times, the player wins a grand prize. Given that the player wins a prize, find the probability that it's the grand prize. So there's quite a lot to unpick here. So we're playing the game 10 times, and we're looking for, as a success, to get a number that is greater than 2. So the probability of getting a number greater than 2, we worked that out in part A. That's going to be 5 over 12. And we know that we're playing this a fixed number of times with a fixed probability. The probability is going to be 5 over 12 each time. And we either get a number that's greater than 2 or we don't. So we have success or failure. And it's going to be independent of what's happened before. Well, that's the perfect condition for a binomial distribution. So if I call this event of playing this game x, and this follows a binomial distribution where you have 10 goes and the probability of success is 5 over 12. So let's work out some of these probabilities, and we'll then talk about how that all comes into finding out the probability it's the grand prize, given that we win a prize. So first thing I'm going to work out is the probability of getting a number greater than 2 at least 7 times. What that means is at least 7 times will mean 7 or more. So we're going to work out the probability that x is greater than or equal to 7. What that means is I want to work out the probability of it being 6 or less successes and then take that away from 1. This is because if I use my calculator, then it won't be able to find 5/12ths in the table, so you will need to use calculator here. If you use your calculator using binomial CD, that will give you the cumulative distribution for all the numbers up to 6 if you put in 6. So if you put in x as 6, you'll get the probability of 0, 1, 2, 3, 4, 5, and 6 successes. So if we work out all the ones that we don't want, so we don't want 0, 1, 2, 3, 4, 5, or 6, and if we take that away from 1, that will tell us the probability of it being 7 or more. So if we do that, using your calculator, say binomial CD on your calculators, it will all differ depending on what calculator you use, so just make sure you're confident with finding probabilities on your calculator. You'll get 0.06821. Now, they win this, so this is the probability that they win the standard prize. But what about the grand prize? Well, we've got to get a number that's greater than 2 at least 9 times, so 9 or 10 times basically. So we work out the probability that x is greater than or equal to 9. what we don't want is 8 or less successes. So we work out what we don't want because your calculator will tell you that value of x that you put in, that all the probabilities up to that number, including. So we want to work out the probability of 8 or less and then take that away from 1. So if we do this, we get the following. And we get quite a small probability. Which makes sense. You know, it should be less likely to get 9 or more than it is to get 7 or more. So now let's kind of break down though what we're actually trying to find here ultimately. Given a player wins a prize, find the probability that it's the grand prize. So what we know already is that they have won a prize. So we're given this additional information that they've won the prize, and we're going to work out the probability that it is the grand prize. So this is going to be some conditional probability, because what we're saying here is find the probability that x is greater than 9 given that you got x is greater than or equal to 7. So we can use our conditional probability formula, which I'll write above here. So the conditional probability formula, you can get this in a rearranged form in your formula book, is the probability of A given B is the probability of A and B over the probability of B. So that's what we're going to do here. We're going to work out the probability that x is greater than or equal to 7 and x is greater than or equal to 9, which I know, well, you might kind of think, hang on a second, isn't that just x is greater than or equal to 9? It is. We'll talk about that in a second. Over the probability of x being greater than or equal to 7. So, on the bottom of my fraction, I'm restricting this to the cases where you win a prize. So that's the probability of x being greater than or equal to 7. So that's going on the bottom of my fraction. On the top of my fraction goes the probability that you get 7 or more successes and you also get 9 or more successes, which obviously has to just mean you get 9 or more successes, because that's the only way you can possibly get, but both of those events can possibly happen. The number has to be 9 or 10. If you get 8 successes, then it meets the first condition of being 7 or more, but it doesn't meet the condition of being 9 or more. So we just put on top here the probability that x is greater than or equal to 9. Just like that. And then we can work that out to get 0.0347, which will make sense that we get a slightly bigger probability of getting the grand prize than just generally getting the grand prize. Okay? Because if you already know the player had won a prize of some sort, that's going to increase the odds that they have won the grand prize. Okay? Right then, on to part C. So, we have just put the table here again, and yet again we'll just put in that we know that A is a 6th and B is a 12th. Now we're told that the independent random variable C1 and C2 each have the same distribution as C. And we're asked to find the probability that C1 equals 2C2. So let's unpick what this actually means. So think of C1 and C2 as the first and second times you play the game. Okay, so C1 is the result of what you get the first time you play the game, and C2 is the result that you get for the second time you play the game. And we're going to work out the probability that the score you got on the first go is twice as much as the score you got on the second go. So we just want to think about the possible combinations of that happening. Okay, so basically you're saying that the first go you get double what you got on the second go. So what that means is we're looking for the probability of getting C1 to be 4 and C2 to be 2. Okay, because if you get a 4 the first time, then the second go, if you got a 2, 2 times 2 for 4. So that's one way this could happen. Or we could get 2 on the first go, which means we just get a 1 on the second go. Okay, so for these events to happen, you need to get either a 4 the first time and a 2 on the second go, or you get a 2 on the first go and you get a 1 on the second go. Now, both of those things have to happen, okay? You have to get the 4 and the 2, or you get the 2 and the 1. So to work out these probabilities, I'm going to multiply the probability of getting a 4 by the probability of getting a 2. Okay, when you've got those AND events, you're going to multiply them together, okay? Because you've got a 6th chance of getting the 4 the first time, and then out of those times, you've then got to then get the 2 as well. So we're going to do a 6 times a quarter. But they're going to add on another way that we can do this. Okay, so we're going to add on the probability of getting a 2 on the first time and a 1 on the second go. So you're going to do a quarter times a third, and we'll work that all out to get an 1/8. Right then, we're going to look at part D now. I'm not going to lie, I'm pretty proud of this question. Okay, I really like this one. You may differ, your opinions may differ, but I was really happy when I came up with this one. So, again, let's just one final time. We'll just plug in that we know what A and B are. And we're told that the random variable D is sine C pi over 2. If you can't quite see that, again, check out the actual full questions in the description. And then F is cos C pi. And we're going to find the probability that D equals 0 and the probability that F plus 2D squared is going to equal 1. Okay, so let's have a look at what on earth is happening here. So what we'll do is we'll just work out some values for D first, just so we can see what this is. So D is represented by taking this number C, so it being getting the outcome of 1, 2, 3, 4, or 5, and you're going to times that by pi divided by 2, and then you're going to do sine of it, and that outcome is going to represent D. Okay, so if C is 1, then we get sine pi over 2. Okay, if we do sine pi over 2, well, that's just 1. If C is 2, then we've got 2 pi over 2, which is just pi. Sine pi is just going to be 0. And to speed things up a little bit, we can draw a sine graph. And we can just see that we're just going up here in multiples of pi over 2. Okay, so we'll have pi over 2, 2 pi over 2, or pi, 3 pi over 2, 4 pi over 2, or 2 pi really, and then 5 pi over 2. So we're going 1, 0, minus 1, 0, 1. So when C is 3, D is going to be minus 1. When D is 4, when C is 4, D is going to be 0. And C is 5, D is going to be 1. So the probability that D equals 0, the only time that will occur is if C is 2 or 4 in the first place. Okay, so if C is 2, then you end up with an outcome that gives you D as 0. If C is 4, then you end up with an outcome that D is 0 as well. And we're just going to keep the probabilities that we already have assigned to C for 2 and 4. Okay, because the probability that you get D is 0 relies on you getting the C to be 2 or the C to be 4. So we're just going to add up the probabilities of a quarter and a sixth here, and this is going to give us what we're looking for. So probability is just going to be quarter, I shall write this below, it's going to be a quarter plus a sixth, which gives us 5/12. Okay, now let's look at part 2. Find the probability that f plus 2d squared equals 1. Okay, this looks a little bit more challenging. So let's look at what f is. F is cos c pi. Now cos, let's draw the graph here for a few more cycles. So we'll be looking at putting c as 1, 2, 3, 4, 5 and then work out the value of f. So that's cos of pi, which will just be -1. And then we'll do cos of 2 pi, so that will just be 1. And then we'll do cos of 3 pi, which is going to go to be -1. And you can see this pattern's going to alternate here. -1, 1, -1, 1, -1. And then what you could do is work out f plus 2d squared. Okay, so we're working out what happens when we do f plus 2d squared. So we do -1 plus 2 times 1 squared. When we do that, we get 1. Then we do f plus 2d squared, so that would be 1 plus 2 times 0 squared. Also 1. Then we do -1 plus 2 times -1 squared, which is also 1. Interesting. We do f plus 2d squared again, so 1 plus 2 times 0 squared, and something funny is happening here because we've got 1 again, and then we do it one more time. We find out actually we get 1 another time. So it's always guaranteed that we get 1 when we do this. So the probability of working this out, that's just going to be 1. Now, there is actually, and you might have spotted it, there's a reason why we're going to always get 1 when we do f plus 2d squared. Let's look at what these actually are here. We've got cos c pi and we've got sine c pi over 2. Well, let's just say let theta equal c pi over 2. Okay, this would mean that 2 theta is c pi. And if we plug that into f plus 2d squared equals 1, well, f is going to be cos 2 theta, and d is going to be, so d is going to be sine pi, but if we do 2d squared, that will be 2 sine squared theta. And if you rearrange this, you'll get cos 2 theta equals 1 minus 2 sine squared theta, which we know is one of our trig identities. So you could kind of look at this and just go, oh, well, okay, it's always going to hold true for any value here, because it holds true of that double angle formulae for cos 2 theta. Now, you don't necessarily have to have spotted that. You could have just done what I showed you before. And I've tried to show you that kind of more just play around with it, because if you can't spot it, you can at least start to work out the terms. But I thought I'd just show you that, mostly because I was just pretty proud of that question, but hopefully you enjoyed it too. Right, spent a long time on question 1. Now let's look at questions 2 and 3. These ones will be a little bit shorter. You'll be glad to hear, I'm sure. In question 2, we're going to look at some Venn diagrams. So we've got students at university are asked about what types of film they enjoy. They are asked whether they enjoy action, comedy or horror films. They select a student at random, and the events A, C and H are defined as follows. So A is that they enjoy action films, C is they enjoy comedy, H horror, and we've given the Venn diagram, but we've not been told P, Q, R or S on this diagram. And the first thing we're going to do is find the values of P, Q, S and R. Possibly an exam question might split this up a little bit more. I think it's off the screen at the moment, but if you see the original document, I gave this like 6 marks to kind of find everything here. These are based on actual questions, so the marks I'm assigning are kind of what I would roughly recommend as a guidance for these types of questions. So this is a 6 marker, so there's going to be quite a lot to find. There are 4 things that we need to find here. So first I'm just going to start setting up some equations. Okay, so we're given these facts here at the top. Now what these facts are is the probability of A is 0.65. So what that means is everything in the circle of A has to add up to 0.65. Okay, bear this in mind with Venn diagrams. When we've got all these probabilities here, if you want to work out the probability of that event, it's every individual part of that, all the individual probabilities within that circle. You need to add them up to find that probability. So the probability of A is 0.11 plus 0.21 plus P plus Q, and that is going to equal 0.65, which we can then simplify to P plus Q equals 0.33. So again, not going to be enough to find what P and Q are just from that. So let's look at some more information here. We also get told that the probability of C and H is 0.23. So that's that intersection between C and H. So what that means is that P plus R must equal 0.23. So let's write another equation here. P plus R equals 0.23. So yeah, again, I've got 2 unknowns in one equation. So yes, you could rearrange to make P and then put that in the first equation, but then you've just got Q and R involved there. So we're going to need to use the third piece of information, and that's that the probability of C given H is 23 over 41. Now I'll remind you again of the formula for conditional probability. So this is a rearranged version of what is in your formula book. Okay, the probability of A given B is the probability of A and B over the probability of B. So let's translate this into C and H. So the probability of C given H, so what this means is the probability that someone likes comedy films given that they like horror films, which we'll explore in a second, about the independence, or whether or not they're independent. So instead of saying A and B, we'll say C and H, and we put this all over the probability of H. Okay, so restricting our sample space to just look at where they are. We're just talking about the ones that like the horror films. So the only people that will like comedy films in the horror circle is going to be the probability of C and H. So the probability of C and H, well, we're given this, that is 0.23. And the probability of H, well, that's everything within this circle of H. So that's the 0.05 plus the P plus the Q plus the R. Okay, and remember, we know that this is all going to equal 23 over 41 as we're told. So we can say 0.23 over 0.05 plus P plus Q plus R is going to equal 23 over 41. However, I know that P plus Q is 0.33. And alternatively, I know that P plus R is 0.23. So what I'm going to do is I'm going to replace the P plus Q with 0.33. Okay, so I'm just replacing this, using this piece of information to replace the PQ with 0.33. So I get 0.38, and I've got that plus R, so 0.05 plus 0.33 plus the r, and that's going to equal 23 over 41. What I can then do is solve that equation to find r. So r is just going to equal 0.03 when I solve that. Okay, you can do the rearranging, but you might just be able to spot that because you've got, you can basically just times both sides by, both the numerator and denominator by 100 here, and then you'll see, oh, actually it's a lot easier to solve this when you do that, and just get r is 0.03. Knowing that r equals 0.03, sub that into your p plus r equals 0.23 equation, and you can find that p equals 0.2. If you know p is 0.2, you can sub that into the p plus q equals 0.33 to get 0.13. The only thing left to do now is to find what s is. Now everything within this rectangle must add up to 1. So I know that when I add this all up, I've got 0.11 plus 0.21 plus 0.26 plus 0.05 plus p plus q plus r plus s is going to equal 1. So subbing in all that I found out there, so adding all these terms together, adding the p, the q, the r together, I get 0.99. So the only one left, and these are people that don't like action, comedy or horror, so it'll be a very small proportion. That's just going to be 0.01. So we've got some slightly smaller questions added on to this. We've got to find the proportion of students who enjoy exactly 2 genres of film out of action, comedy and horror. So that means they only like 2 out of the 3 exactly. Okay, so this would just correspond to the people that like action and comedy but don't like horror, because they only like exactly 2. So if it's action, comedy and horror, then that's all 3 types. We're not including that. So either action and comedy, action and horror, or comedy and horror, and then we'll just add them together and we get 0.37. So only 1 mark, it's only just a quick little add on there. Part C, we're asked to determine whether or not the events A and H are statistically independent. We're going to clearly show our working here. So to show if 2 events are independent, when we multiply their probabilities together, they give us the probability of both events occurring. So the probability of A times the probability of B would equal the probability of A and B, okay, if they're independent. Basically, the chance that one has happened doesn't impact the probability of the other. So to do this, we already have been told that probability of, we're looking at action horror. So the probability of someone liking action is 0.65. The probability that they like horror, that's everything in this circle of H added together. So that's going to be 0.41. And then what I need to do is work out the probability of A and H. So the probability of A and H is everything in the intersection of the circles between A and H. So that's 0.13 and 0.2. So that's just going to be 0.33. Now, to determine whether they're independent, I'm going to need to perform the calculation of the probability of A times the probability of H. And when I do that, so that's 0.65 times 0.41. When I do that, I get 0.2665. Okay, you must show this calculation. Okay, when you're doing these types of questions, don't just talk about it verbally. Well, not verbally. Don't just write it down. Make sure you're actually backing this up with, the maths here. So the probability of A times probability of H is 0.2665. The probability of A and H is 0.33. So we can conclude that 0.2665. Make sure you do some sort of comparison of numbers. Because these numbers are not equal to each other, we can conclude that A and H are not independent. Okay, now I'm not a film expert by any means, but I can imagine if you've got a preference of one film, that might make you more or less likely to like a different type of film as a result of that. Now, I just made these numbers up, so I'm not saying this is going to be completely accurate, but you'd probably imagine that, if you like comedy films, you might be less likely to like horror films. Possibly, I don't know. Yeah, again, not a film expert, you might be. There will be people that like both, but I would imagine that a preference on one would impact whether you're more or less likely to like another one. Now, part D, we've just got to work out the probability of, and I'll write this out bigger so you can just see if you've not got the actual question open at the moment. So we're working out this. So what we're going to do first is we'll work out what's actually in these square brackets. Kind of best to start with that. So I'll just rub that all off again. So we've got the probability of C or H. Now, C or H is everything within these circles, okay? It can be both things, okay? But as long as one of those situations is happening, then it will be included, okay? So what I've highlighted there is C or H, okay? But then outside those square brackets, you've got this dash, which means not C or H. Okay, so actually everything that I've shaded there is what we don't want. So the only things we do want are the 0.11, okay, because this would be where C or H isn't happening, as well as this 0.01 here as well. So the probability of it not being C or H would just be those that exclusively just like action, or those that don't like any action, comedy, or horror. So just adding the 0.11 and the 0.01 together. Okay, on the home straight now with the last question. So runner has a training session where they run a mile, and if this mile is ran under 7 minutes, they run another mile. They repeat the system until they've either failed to run under 7 minutes or they have ran 4 miles in total. The probability the runner can run the first mile under 7 minutes is P. After each mile, the probability they can run each mile under 7 minutes decreases by 10%. Now, there's a lot going on there, which can seem very confusing. So my best advice is let's get that in some sort of a tree diagram. So what we're going to do first is we're just going to start here by saying they either do run the mile under 7 minutes, which I'm just going to call that S for success, or they don't. Okay, so the probability they do run under 7 minutes, we're just going to call that P. So if they don't do it under 7 minutes, then we're going to call that 1 minus P. Now, if they don't run under the 7 minutes, under the 7 minute mile, they stop there. So I'm not going to continue any of the branches beneath here. I'm just going to continue with the case that they do succeed. So if they succeed in running the first mile under 7 minutes, then we're told that if the probability of them running the next mile under 7 minutes decreases by 10%. So the probability would now be 0.9p. Okay, so it's just 90% of the previous probability. So the probability that they don't do that will be 1 minus that. Okay, either they do this or they don't. So you've got that situation there. And this continues in that if they run the first 2 miles, then the probability of running the third mile under 7 minutes is now 90% of the previous probability, or 10% less of the previous probability. So we times 0.9p by another 0.9, and we get 0.9 squared p. And the probability they don't do this will be the following. Okay, and then they go for a fourth. If they do get the first three, then they go for a fourth mile. And then we times that previous probability by 0.9. So now it'll be 0.9 cubed p, which you could work out. I'm just going to leave it in terms of 0.9. You'll probably see why that is in a second. And the probability there that they don't do that will be 1 minus 0.9 cubed p. Okay, now if we're told that they stop if they fail to run the mile under 7 minutes, or if they have ran 4 miles, they'll stop. Okay, so we don't need to go any further. So we're told that the probability they start the 4th mile is 0.157464. Okay, very unique number, but I purposely chose that so the numbers would actually work out nice in the end for us. So in order to start the 4th mile, we must be successful with the first 3. Okay, so it doesn't matter whether we actually complete that 4th mile or not under the 7 minutes. We just need to make sure that we've been successful on the first 3 miles. So that would just be multiplying p times 0.9p. Okay, so the probability we successfully run the first mile under 7 minutes times the probability of us doing that for the 2nd mile, which is 0.9p, times the probability that we do that for the 3rd mile, which is 0.9 squared p. Okay, which you might, I'll be honest, you might have worked this out without the tree diagram, but it should help, and with the next question as well, it might help as well. So I do believe this helps to just visualize the problem, but maybe you have worked it out without it, but I think it helps in my opinion. So if we work that out, we get 0.9 cubed times p cubed. Okay, just times together those 0.9s and the p's there to get that. Yet again, you could work out 0.9 cubed if you wanted to at this point. I'm just going to keep it like that to make it a little bit nicer. So we know that this probability is equal to 0.157464. And if I divide both sides by 0.9 cubed, I get 27 over 125. Okay, now you might see why I purposely picked 0.1574464 as this probability. When we cube root this, we'll get p as 0.6. Okay, and that will be our value of p, and that's part A done. Part B, we're asked to find the probability that the runner stops after the 3rd mile. Okay, find the probability that the runner stops after the 3rd mile. So on my tree diagram, let's kind of just look at the route there. So if they stop after the 3rd mile, they had to be successful for the first one, successful for the second, and failed to do the 3rd one, okay? Because they're stopping after the 3rd one, which means they're not going on to do the 4th. So we're just going to follow that pathway through of p times 0.9p times 1 minus 0.9 squared p. And when we do that, with our value of p being 0.6, we get 0.166536. Okay, we could simplify that a bit. Okay, as long as you work into at least 3 significant figures, that's fine. Then we're told the runner uses this training session each week for 5 weeks. By using a suitable model, find the probability that the runner reaches the 4th mile in over half of the sessions. What we have yet again, like we had in our first example, we have a binomial distribution. Okay, we're doing this for 5 weeks, and the probability they reach the 4th mile each time is going to be fixed at 0.157464. Now, you may argue that probability might not actually be fixed in reality. You'll get to argue that in part D. But we're just modelling the situation here. But there might be some scope to talk about why this isn't necessarily suitable. We'll talk about that in part D. Now, if we want to find the probability they reach the 4th mile in over half of their sessions, well, that would mean that out of the 5, they would need to be successful in 3 or more of those sessions. Okay, if you succeed in 3 out of the 5, that's more than half. Okay, same with 4, same with 5. So to work out the probability of being greater than 3 or more, you work out the probability 1 minus the probability of being 2 or less. So yeah, again, you can use your calculator here with binomial CD. You'll certainly need to, because you won't find 0.157464 in the tables. So you can work that out to get 0.0304. And then for the final part, we're stating one limitation of the model in part C. So I kind of alluded to it earlier. We're assuming that probability is going to be fixed. So I would write something along the lines of we are assuming the runner. So, if they improve, we might expect their probability to go up. So we're assuming that the runner does not improve. Now, if they were to improve, you'd expect the probability of them getting to that 4th mile each time to increase, okay, rather than stay fixed out of the 5 weeks. Alternatively, we could also argue we're also assuming that they don't get fatigued. Okay, so if they got tired and they just struggled each time to get to that 4th mile, then that would impact our probability. It would get less in that case. But either way, we're assuming that the probability stays fixed. So we're assuming that the runner does not improve or get fatigued. You wouldn't have to say both. You could just say one of those 2 points in the exam. And that the probability of getting to the 4th mile remains the same each week. Okay, and that will do it. This one's gone a lot longer than I do intend these to go. But to be fair, probability, it's one of my favourite topics, and I've maybe got a little bit carried away with some questions that perhaps a bit more on the challenging side. But, I hope they actually will really help you. Just doing some probability practice, as well as just sneaking some other things in, like some trig and other things like that. So let me know if you want a little bit more input with some of these or struggling with them. The next video, and if you want to return to pure, we're going to return to it in the most purest of topics in terms of proof. Okay, so proof is going to be our next video. In the description below, I'll put the questions for proof there, so you can start having a go ahead of that video. Probably a little bit short to that one as well. But yeah, again, I know proof is a topic a lot of people struggle with, so I think that's going to be a really helpful one for you to do. If there's any particular topics you'd like to see in future weeks, let me know and I'll have a look at that. But keep doing maths, keep practicing, and I'll see you in the next video.